Good afternoon, everyone. I hope that you're having a great win Thursday. How about Thursday? And what's that? I don't need that. Um, so I have finished the PowerPoint for tomorrow. I'm going to post that, or I believe that I posted that as well as the PDF. Um, Before we kind of get moving, is there anyone who's having any issues navigating our Canvas page at all? Finding things or anything like that. In the event that you are, please don't hesitate to send me a message, and I'll do my best to take care of that and help you out. Um, with that in mind, though, I don't want that file. I want this file. I post the PDFs because it seems like when people are using a tablet, it's much easier to access a PDF. You don't have animations and stuff, but I very rarely use a PDF, but I sometimes get mixed up and I upload those. Okay, so today we are getting into amino acids. Now, if you've talked to anyone who's taken a biochemistry class before, it's kind of amino acids to me kind of have the same reputation as um, organic chemistry. And what I mean by that is if someone says, "Oh, well, I'm gonna, go to pharmacy school or I'm gonna go to PA school or medical school," then there's someone in their life who says, "Oh, well, organic chemistry, it's tough." Um, and then I don't know, like I struggled with organic chemistry, but it was not like absolutely overwhelming. Um, and I kind of feel like amino acids have that same sort of reputation because it's like, oh, well, that's one thing that you can kind of look at and say, oh, well, this is going to be challenging. It is. But there are some strategies that we're going to talk about today, and some ways in which you can approach the study of amino acids and kind of be gracious and patient with yourself. In addition to that, what we're going to be focusing on is how you can basically stack the deck in your favor. And what I mean by that is um, how you can look at amino acids and begin to understand them a little bit more easily. So, first and foremost, what are amino acids? Amino acids are molecules with both amino groups and acidic groups. One thing that you might recognize is whenever you're talking about an amino acid, you're going to notice something like this, NH3 plus, and you're also going to notice something like this, an amino group and a carboxylic acid. So essentially, if you have these two functional groups on a molecule, it's kind of classified as an amino acid. Now, with that said, the most notable and kind of common amino acids are the ones that are, or the way that most amino acids are well known is that they are the building blocks of proteins. So they are the subunits that are assembled together to make a polymer or a protein or a polypeptide as a polymer. These specific amino acids are known as proteinogenic amino acids. Now, when it comes to the proteinogenic amino acids, there are a total of 22 proteinogenic amino acids. Now, of those 22 molecules, there are tons of derivatives of them because they can be, I'll say, they can be modified. And they can be modified both enzymatically and chemically. So when you talk about amino acids, we have these kind of general sort of basic structures, the kind of boilerplate type of structures, but then they can undergo modifications. And those modifications will include something like, well, adding a methyl group. Okay. Now, with that in mind, not all amino acids are used as building blocks for proteins. These are known as your non-proteinogenic amino acids. Now, let me circle back to this number 22. I don't know that that's necessarily a controversial number, but in some resources, in some textbooks, and some um, references, you might look at your list of proteinogenic amino acids and you'll only see 20. We're only going to talk about 20 of them. The reason for that is two of the, or the kind of the last two, I guess you could say, are not nearly as common as the first 20. What we're going to be focusing on is our 20 proteinogenic amino acids. There are a total of 22, but we're going to focus on the primary, the main 20, to put it simply. Okay, now let me do one thing. Get my chat box up. There we go. Okay, there we go. Now, when it comes to those non-proteinogenic amino acids, what role do they play? If they're not, if an amino acid isn't going to be used um, for synthesizing a protein, what's it going to do? Well, if we look at this molecule right here on top, not that one, not that one, not that one. Oh, wow, I just ruined the movie right there. This molecule right here is known as ornithine. Add to the chat if you think you know what organism ornithine was extracted from or first found within. I'll give you a hint. That's right, birds. Because the study of birds is, after all, ornithology. And if you didn't know that word up until now, you're welcome. So, ornithine is a non-proteinogenic amino acid, and it was originally extracted from birds. Neat. Nice little kind of bar trivia type of question, or bar trivia type of information that you have there. Now, well, if we look at that molecule, we've got an amino group and a carboxylic acid. Done. It is an amino acid. Where is, or what is ornithine used in? What is it found in? Well, ornithine plays a key role in a process known as the urea cycle. Does anyone know what the urea cycle, or let me go this way. Hit a number if you have heard of the urea cycle, a letter if you have not heard of the urea cycle. So a number means yes, I've heard of it, and a letter means no, I've never heard of it. Okay, great. For those of you who haven't heard of the urea cycle, it's a critical cycle that, or process by which humans take care of excess nitrogen. They take nitrogen, package it together, make urea, are able to excrete and process urea. So the urea cycle involves lots of movement of amino groups. And one of the intermediates in this process is ornithine. Another non-proteinogenic amino acid happens to be found in the same process is known as citrulline. Amino group, carboxylic acid. Citrulline, right there. So ornithine and citrulline are both non-proteinogenic amino acids, so they're never going to be integrated as a part of a protein, but are they essential for, well, maybe not essential. Let me rephrase that. Are they super important for overall human health? They are. Because if you don't have ornithine or citrulline present, what's going to happen is, well, nitrogen's going to accumulate. And I think that one thing that can happen is you can have goiters. There's a couple of other, I guess, health related issues that can surface. So when it comes to a discussion of amino acids, what I want you to do is think about that very broad field, that that big umbrella of amino acids. And right now we're going to have two kind of sub umbrellas, or hierarchically, if you wanted to think about it, we've got two different categories: amino acids, cut in two. One half is proteinogenic amino acids, the other half is non-proteinogenic amino acids. If you think about amino acids in this sort of way of like constantly dividing and conquering, I think that's going to really help you out because that's what we're going to do through this lesson, tomorrow's lesson, and just kind of, well, anytime we talk about amino acids. We are most interested in proteinogenic amino acids. This right here is their backbone. Their backbone has an amino group over here, carboxylic acid. Okay, fits the billing of a amino acid, but next up is this carbon in the middle. This is known as an alpha carbon. Anytime that you have maybe let me think of the best terminology here. Your carbon next to a carboxylic acid, that's going to get the Greek letter alpha. So that's in effect kind of your first carbon in some respects. Now, when we talk about proteinogenic amino acids, more times than not, we are very interested in alpha amino acids. So to, take a step back, if you've heard of amino acids before, people are typically talking about proteinogenic amino acids. Okay, now let's peel back one more layer of the onion. Not only are they talking about proteinogenic amino acids, but they're talking about alpha amino acids. These alpha amino acids have an R group. That R group is what's going to differentiate all of our proteinogenic amino acids from one another. But this is our general backbone. Now, the way that I've drawn this, with respect to protonated or deprotonated or partially protonated, what do you think is the best term to use to describe this specific structure that I've got with the backbone that I've drawn? Add it to the chat. Protonated. You're absolutely right. So this molecule is protonated. Now, with that in mind, there's a couple of things that I want you to think about. So I'm going to write some details about this structure. One truth about this structure is that it is, I'm going to add, fully protonated. Now, the R group that I've got down there, I'm just going to kind of suspend considering that because that R group is what's going to differentiate all our different amino acids from one another. But with respect to the functional groups that we have, it is a fully protonated molecule. Now, the next statement, I'm actually going to kick this back to you guys. Based on what you see, based on what I've drawn, what's the charge of this molecule? +1. Now, I see people responded with positive. Correct. I want to add one more detail to that, and that is to emphasize the magnitude of that charge. This molecule has a charge of +1 as opposed to +2. So when we talk about charges of amino acids or of polymers of amino acids, we want to be able to say, well, this has a charge of +2 or this has a charge of +3. Okay. So those two things are true about this. And then the third item and the last item, you're not going to really pick up just from looking at this picture, but instead you're going to pick it up from looking at this picture and looking at our two pKa's. Well, we know that this is in a solution with a pH below 4.8. Now, was 4.8 arbitrary? No. 4.8 is the pKa of that carboxylic acid or of that carboxyl group. It's fully protonated. So, more than likely, this is at a pH of below 4.8. Now, with that in mind, whenever I draw an amino acid, and I recommend that you do this, is I am going to draw it fully protonated. So what I'm going to do, another way of putting that is I draw my amino acids at a pH of 1. Basically, everywhere that a proton can be, it is. Can I get a number if, yeah, that makes sense, or a letter if I'm confused? Okay. So this molecule right here, I'm going to start on this end. That nitrogen, one thing that we know about nitrogen is nitrogen likes to have three bonds and a lone pair of electrons. If nitrogen has four bonds to it, then nitrogen's going to have a positive charge. Okay. Now, or ammonium, for example, or ammonium versus ammonia, that's going to have a fairly high pKa. This group, this N-termini, this amino group, has a pKa of 9.3. So that representation right there tells me that, okay, it's fully protonated. That nitrogen has four bonds, it has a positive charge. The pH that this molecule is in is going to be below 4.3, or sorry, 9.3. Now, if we go on to my C termini, that too is fully protonated. Everywhere that I could possibly put a proton, I've got one. This doesn't have an overall charge, or this carboxyl end does not have a charge. It has a pKa of 4.8. Now, to keep 4.8 and 9.3 straight is going to be a little bit tricky. So my default is going to be, let me add this as a item. I draw all AA fully protonated. That's the first thing that I'm going to do. Anywhere I can put a proton, I'm going to. Then, so another way of putting this is I draw them at a pH of 1. Now, I don't want anyone to think like, well, why not 1.5? Why not 0.5? I pick 1 as just my kind of effectively my lowest possible pH. So the molecule that I've got up here, this is what the molecule is going to look like in an extremely acidic environment. Now, that's just my backbone. Before we proceed from here, it's important that you understand the directionality of a protein, a polypeptide, and an amino acid. All are going to have the same directionality, but if you're to look at this molecule and you're just describing the way that it's displayed, just like you read in English left to right, I've drawn this peptide showing that same directionality, and I'm moving from the left to the right. What we refer to that as is not left to right, but instead, we read an amino acid or we read a peptide in N to C directionality. So I'm reading it from what's known as the N termini to the C termini. Now, that's going to be much more important whenever we're looking at peptides. But for the time being, I think it's good to be able to identify, oh, this is the N terminus, this is the C terminus. Okay. Now, the backbone of a amino acid is going to undergo changes. This over here, where I'm putting an X, is where my pH is 1. We are going to, as we add more base, plus OH, and make this environment slightly more basic, we're going to add hydroxide ions, and we're going to deprotonate one of those groups. Which group are we going to deprotonate first? Are we going to deprotonate? So our pH is gradually increasing. We're going to deprotonate the group with the lower pKa. pKa of 4.8 versus a pKa of 9.3. So just imagine that I'm titrating in a strong base, potassium hydroxide, sodium hydroxide side. I'm adding base, and the first thing that I'm going to do is I'm going to remove this proton from my C termini. The resulting molecule, whenever I remove that proton, is the one that you see here in the middle. Now, just as I asked the question on the previous slide about charges, can you tell me in the chat what is the charge of the molecule in the middle, where I have the star above my molecule? I've got 0 and neutral, and you're absolutely correct. We have two different charges, positive and negative, but they effectively cancel one another out. So it's important that we think about the net charge. So the net charge of this molecule, I'm going to label it as NC, net charge, is 0. Now, this specific form in the middle here that has both a positive and a negative end to it is also known as the Zwitter ion. It's the Zwitter ion form of an amino acid, where you have both a positively charged region and a negatively charged region simultaneously. That might seem like, oh, but how's that possible? Well, that's possible because we have two different functional groups. We have a carboxylic acid, or a carboxyl end, and we have an amino end. Those two groups have two different pKa's, which is why when we're in a pH of, let's say, 7, if our solution's pH is 7, that pH is higher than our 4.8, but lower than our 9.3. Okay. Now, before I proceed to the last one, does anyone have any questions about the transition from our molecule on the far left to our molecule in the middle? Add a number if, no, I'm good, or a letter if, eh. And if you'd like to add the letter, go ahead and also send a follow-up message that, hey, here's my question. Good. And just a little suggestion, um, if you, if any of my prompts and questions like, oh, I'd like to respond, but I'd like to have it as a private message, I hope that you know that you can go into the chat and send the message directly to me as opposed to the entire class. Um, so feel free to adjust that if you want. And, if I'm talking and you have a private question that you've got, go ahead and send it to me. I might pause to then have to read it, but go ahead and send it to me. Okay. So our third form of our molecule is the one that we've got on the far right-hand side. How did we get that? Well, what's happening is when we go from this molecule over here that I got labeled with X to then our Zwitter ion form, we added more base and removed a proton from the C termini, from the C carboxy termini end. Then what we're going to do is continue adding, lo and behold, more base. And as we continue to add, are we doing anything else to the C termini? No. We've removed the proton. So is any other part of the molecule going to be affected by adding more base? Absolutely. The N-termini of our molecule is going to be impacted. After we have removed all of the protons from the C-termini end, and whenever I say all of the protons, I mean we're not dealing with just one molecule. We've removed all of the protons from all of the molecules on the C-termini end. Then what we're going to do is start to go here and look at the N-termini, our other ionizable group. We have two groups that are ionizable. We have to completely take care of one of them before we can move on to the next one. And whenever we do that, whenever we've removed all of the protons from the C-termini and then removed all of the protons from the N-termini, we end up with this molecule down here. Add to the chat, what is the overall charge or the net charge of this form of the molecule found on the far right-hand side? Wonderful. Wonderful. -1 is the correct answer. So to rehash that, the backbone of a proteinogenic amino acid can range from +1, 0, and -1. Thinking about just the backbone, can the backbone have any other charges? Could it ever be +2? No. Could it ever be -2? No. The backbone of every single proteinogenic amino acid is diprotic, or is a diprotic acid. There are two ionizable groups, the N-termini and the C-termini. Now, does that mean every single amino acid is a diprotic amino acid? It does not, because the part that we didn't really neglect, but didn't account for and didn't consider is this group right here, the R group. Those R groups are arguably the most important part of an amino acid because those are what differentiate different amino acids from one another. Now, with that in mind, we've neglected that. We haven't thought about that yet, or we haven't worried about that and focused in on that. But that's the most important part. Yes and no. If you understand the principle of what we've just gone over here, two ionizable groups at a pH of this compared to your pKa's, it's going to have a charge of this. At this pH, it's going to have a charge of this. It's going to have a charge of this at this pH. If you understand that and can conceptualize and appreciate that, that puts you in a very good position to move on to talk about other things related to amino acids. Now, I'm going to go ahead and proceed where I'm going, and we're going to unpack our 20 proteinogenic amino acids. Remember what I said, there are 22, but we're going to be focusing in on the most common 20 proteinogenic amino acids. Now, to process all of those 20 proteinogenic amino acids, I think the best approach is to take kind of a divide and conquer approach. An effective way to divide those 20 molecules is to think about them in terms of their kind of chemical nature. All of your proteinogenic amino acids, this definition right here, this item right here, this label, polar. Do you think that this is applied to what I've just circled right here? Add a number if you say, yeah, that's where our definition for polar or non-polar comes from. Add a number if you think it's that. Add a letter if you think, I think it's something else. Seeing letters. Great. You're absolutely right. Why is that? Well, because what I've circled is the backbone. If you look at all of these amino acids, I've circled the backbone for serine. Now I've circled the backbone for asparagine. Are there any differences between those backbones? Nope. Those backbones are absolutely identical. What differentiates them from one another is this right here, the R groups. Now, those R groups are what make or what give us these 20 protein-genic amino acids different classifications. We've got our polar amino acids and our non-polar protein-genic amino acids. Now, with that in mind, if you try to process all 20 of these and memorize all 20 of these and know these structures, it's a lot to process. It's a lot to kind of digest. What we're going to do is break this down. What I want you to kind of visualize is, we've got that umbrella or that big amino acids, proteinogenic, non-proteinogenic. We've gone in this direction to our proteinogenic. And now we can break those into polar and non-polar. I don't want you to get overwhelmed with the details of either of those right now because we're going to now look at some of these other amino acids, or we're going to look at all of them without kind of getting overwhelmed by memorizing all of them. Now, what I want you to do is try to take this big concept of amino acids and make it smaller and smaller and smaller and smaller. So when you look at these two groups, are there any other groupings that you can visualize from looking at those structures? Now, with that in mind, before anyone answers, I want to give you two hints. One hint is that of these amino acids, of these 20 amino acids, there are 3 that are similar enough that they can kind of have like a subcategorization. Now, what makes that subcategorization a little bit complicated is that there are some that are polar in this subcategorization and some that are non-polar. Now, I'm trying to lead you on a little bit with this question, but I also don't want you to just sort of like flounder and I don't know what you're looking for. So I'll give you a little bit more kind of insight. We've got our polar residues over here. I'm going to draw my X. If I'm looking at these, it's a lot to process. It's a lot of information. If I look down at this one right here, this is an amino acid commonly known as tyrosine. What does anyone notice about the R group of tyrosine? It's a benzene ring. There's one other little thing about that benzene ring with it. Exactly. It's a ring with a hydroxide. It's a phenyl ring. Now, if we look over at our nonpolar amino acids, over here, does anyone see any amino acids that are in this nonpolar categorization that also have rings or a ring? You guys are probably seeing these two right here. Tryptophan and phenylalanine. Those 3 rings or those 3 amino acids come together to make a grouping known as aromatics or aromatic amino acids. Now, I bring this one up and I highlight this one just because of the fact that, well, there's one that's a polar residue, or it's classified as polar, and then a pair that are non-polar. But with their powers combined, they make a kind of subcategorization of your aromatic amino acids. And those are kind of unique because of their aromaticity and their aromaticity and what they do with respect to light, which we will get to, I believe, next week. So now what I want you to do is kind of think, okay, well, how could we classify amino acids? How could we break them up? Well, one way that we could go is polar and nonpolar. Another way we could go is aromatic, non-aromatics. If we were to do that, well, that's 3 versus 17. So that's a lot to process. But I want you to be notified of these because we're going to come back to these next week because of their value with respect to analyzing amino acids. Okay, now what we're going to dig into more today specifically are your polar amino acids. If we look at the polar amino acids, there's a total of 11 amino acids that are classified as polar residues, looking at the blue cell on the left-hand side. I'm going to jump over here, and I want you to look at these and tell me, do you notice anything, or actually, I'm sure you notice things, but add to the chat anything that you notice about two or more amino acids that are classified as polar, specifically looking at their R groups. And I'll get your wheels turning a little bit. One thing that I notice is that, well, this R group for arginine has a nitrogen. So too does glutamine. Okay, that's one thing that's worth noting. I'm going to erase that. And I hope that this picture is a high enough resolution for the screen that you're looking at so that you can see all those. Now, when we look at these polar residues, one of the things that I want to draw your attention to is right here. NH3 plus. And then over here, a nitrogen with 4 bonds to it and a positive charge. Then over here, a nitrogen with 4 bonds to it and a positive charge. These amino acids, these 3, that's something they all have in common. A positive charge on the R group. So how do you think we could kind of come up with a subcategory, a subgroup of those? What do you think we would refer to it as? Polar, yeah, they're polar amino acids. How about polar positive? I think that's a pretty reasonable approach. These 3 amino acids are our polar positive amino acids. Now, you might be thinking, well, how are they classified as positive? Because wouldn't that charge change at a different pH? It absolutely would. These are defined as polar positives. These 3 are polar positive because the R groups are positively charged at a neutral pH. Now, before we proceed, those 3 that you're looking at there, um, is that what those amino acids look like completely at a pH of 7? So the R group Yeah, that's what the molecule looks like at a pH of 7. The N-termini with a pKa of 9.3. Yeah, that's going to be protonated at a pH of 7. Is the C-termini going to be protonated? Yep, you're absolutely right. This should be deprotonated if I were drawing it at a pH of 7. But like I said previously, to normalize and standardize things, I draw these molecules fully protonated. I draw them at a pH of 1 because then I don't have any question of, well, should I add a proton? No, these are fully protonated. That gives me the kind of ease of, okay, well, I'm going to look at my different pKa values, and this is going to be deprotonated depending on the pH. Okay, so these three amino acids are our polar positive amino acids. So I want you to remember lysine, histidine, arginine, polar positive amino acids. Now, next group. Sorry, actually, yeah, polar positive. The next group that I'm going to draw your attention to are these two down here. Aspartic acid and glutamic acid. These are our polar negative amino acids. Why are they negative? Well, these R groups, this one and this one, they would be deprotonated at a pH of 7. Now, with that to say, what I'd like to do here is jump ahead a little bit. And not really jump ahead, but kind of go with the next logical progression. Let's look at these polar amino acids, or these polar negative amino acids, aspartic acid and glutamic acid. Has anyone ever heard of it and add a number to confirm yes and add a letter no? Has anyone ever heard of single letter or three-letter codes for amino acids? Okay. So single letter and three-letter codes are a shorthand and easy way to associate amino acids with, or to identify amino acids. Aspartic acid and glutamic acid. The single letter codes for those are D and E. The three-letter codes for those are ASP and GLU. Now, those single letters and all of the single letters that we're going to be talking about might seem a little bit odd, but I've got screenshots of the papers that came from, or the publications that came from the Journal of Biological Chemistry in 1966 and 1968, respectively. And I've got this picture in the upper left-hand corner. This is a woman by the name of Margaret Oakley Dayhoff. Let me ask you this. Did computers exist in the 1960s? Yes or no? Yeah, they did. Spoiler for if you wanted to time travel. They did exist. And what do we know about computers? Yeah, they were not cheap. You know, I don't know if I think it was an ENIAC, which was probably well before the 1960s, but they were computers that could do what a four-function calculator did, but of course they were like the size of a room. Well, Margaret Oakley Dayhoff was a bioinformaticist, and she was a chemist. She was a physical chemist, and she studied protein folding. So protein structure back in the 1960s, well, 50s. I think her career began in the 1950s and continued on through the 1970s. So she was basically a computational biologist, computational biochemist back then, which personally that just blows my mind because computational biology and structural biology is like, wow, that's an abstract, tough field. And I'm saying that from having the internet and being able to look at a picture of a protein that someone has already worked out. She, however, was in a position where it was like, you want to study protein structure? Okay, cool. Well, we have a room that can do what a four function calculator can do. Great. I bring all this up because she is the reason, or one of the primary reasons, that we have three-letter and single-letter codes for amino acids. Because what she would do is she would write software that would analyze a protein based on its sequence. And instead of writing the full names of every single amino acid out to give the sequence of a protein, she said, it'd be a whole lot easier if we could use like some sort of shorthand notation. And that's where this came from. So these single letters and three-letter codes were adopted to make writing the sequence of a protein easier. Now, if you look at it, and if you look at the name aspartic acid and glutamic acid, looking at those two names, well, I see the letter D in aspartic acid. I'm not looking too closely, but does anyone see the letter E in glutamic acid? Nope. And, somebody might chime in and say, oh, but what about glutamate? Yeah, you're not totally wrong. But that's not where it came from. These single letter identifiers, where they came from was in these papers, they cooked up a couple of simple rules. And they said, can we use the first letter of the name to identify the amino acid? Well, for aspartic acid, what's the first letter of aspartic acid? A. Okay, yeah, we could try that. But if we go back a little bit and we look at all these amino acids, what about alanine? How are we going to identify alanine? So there's a conflict there. Fortunately, there's only 20 proteinogenic amino acids, and in the English alphabet, we've got 26 letters. So we've got some flexibility there. So whenever they were coming up with these guidelines and rules, they said, can we use the first letter of the name? If the answer is yes, done. If there was conflict, then what they would do is they'd say, okay, well, how is this amino acid pronounced phonetically? We use phonics, the sounds. So aspartic, this TI, effectively, that's where the letter D came from as the single letter identifier. That might seem like a little bit of a stretch, but I assure you that's what is in these here papers. Okay, well, glutamic acid, where does E come from? Well, that was not use of phonics, but instead, let's look at the R groups of aspartic acid and glutamic acid. Add to the chat, what's the difference between those two R groups? CH2. Would you agree with me, or would you grant me the idea that, well, glutamic acid is kind of a natural extension of aspartic acid? It's slightly longer, but other than that, they both have the same functional group. They both have a carboxylic acid. It's CH2 and then COOH, and then it's CH2, CH2, and COOH. So by looking at the structures and saying, okay, well, this is a natural progression of this, then what people said was, well, it seems to me that the easiest thing to do would be to link the structures and their single letter identifiers to one another. So where do we go after the letter D in the English alphabet? To the letter E. And that's where that came from. So there are a set of rules and guidelines that were used to come up with these letters, these single letter identifiers. Now, I don't want you to stress about, well, what are the single letter codes? or sorry, I don't want you to think and stress about, well, why are the single letter codes this or this? I instead think that by telling you how they were come up or how they were determined, it gives a little bit of an idea of, sorry, it gives you a little sense of, okay, well, here's how we can move forward. And if you're ever like taking a test or a quiz and you're stifled and you're like, I can't remember what this is. Well, you can default to, okay, is the single letter available? Do we have a conflict? Okay, cysteine is one amino acid, and then oh, there's no other amino acids that start with the letter C. Okay, cool. I'm going to go with that. So we have these single letter and three letter identifiers. I think that it's extremely valuable and worth your time to learn the single letter codes and be able to basically go from the single letter code to the structure and back and forth. Now, with that in mind, what I want to do here is talk about the ionization of these different amino acids. And I'm going to go ahead and jump onto aspartic acid. So, what I want to do with aspartic acid is a couple of things. First, I want to ask you, if I gave you this structure and I said, what pH is this drawn at from A, B, C, D? Cannot be determined. Thirteen, 9, 1.5. This is a multiple choice question. This molecule shown here, which of the following is the pH in which this, or the pH of the solution in which this form of the molecule is shown? A, 1.5. You're absolutely right. Okay. Now, the next question is, what is the overall charge of this molecule? And it would be a multiple choice question if you're a quiz or a test, but what is the overall charge of this molecule? Perfect. +1. Okay. Now, this table right here shows the pKa values of all of the different functional groups on our amino acids. And anytime you have a question on an exam with the pKa values, I'm going to give you those pKa values. I'm going to have a set or a series of pKa values that I will provide you with, and I want you to use those for your calculations or any calculations that are relevant to this. So we've got a charge of +1. The form that I see here is drawn at a pH of, or in a solution with a pH of 1.5. My next question is aspartic acid, the single letter code D. That row has all the pKa values that I need. 9.82, 2.10, 3.86. With three different pKa values, this is kind of before we draw it out, three pKa values, how many different forms can this molecule take on? Or how many different forms of this molecule exist? And think about this fully protonated form as one possible form. I see 2, then I see 3, and I'm still pausing. Still pausing. Somebody's going to do it. Oh, nope, other way. 4. Absolutely right. Absolutely right. Okay. Now, that was a tricky question, but I think a good summary sort of question. What we're going to do now is draw those 4 different forms. I'm going to start in the lower left-hand corner, and I'm going to redraw this fully protonated form. Anytime that I draw an amino acid, what I always do is I draw my backbone, NCC. This is a fully protonated molecule, so I'm going to write NH3 plus. Next up, and if at any point you get hung up, please tell me. After that, I've got my alpha carbon. My alpha carbon is going to have a hydrogen, but it's also going to have an R group. I'm going to fill in my backbone before I go back to the R group. Now I'm going to show you. Maddie, that's a great question. We're going to work through that. I'm going to show you all of those 4 different versions or 4 different forms. But to answer your direct question, how do we know it's 4? Well, if you have a molecule with 3 pKa's, it's going to have 4 different forms. If you have a molecule with 2 pKa's, it's going to have 3 different forms. And I'll illustrate those in just a second so that it's maybe a little bit more clear. And so here's my backbone. Now what I'm going to do is work on my R group. H2. Okay, give me a number if you agree. Yes, that's my form where it's fully protonated. Okay. Now, what I'm going to do is I'm going to switch colors. I'm going to go to blue, and I'm going to give you the pKa values. So this, I'm going to say this is drawn at a pH of 1. My pKa's do not change. My solution pH will, however, change. So this is extremely acidic environment. My N-termini has a pKa 9.82. So I'm going to write 9.82 over there on the left-hand side on the N-terminal of my molecule. If I'm going to go to the C-termini, the carboxylic acid, I've got 2 carboxylic acids. So whenever I see pKaCOOH, it's important to remember, that is in reference to this group right here on the right-hand side of my molecule. That's 2.10. My last pKa value, check, is my R group, 3.86. Check. Okay, I'm going to throw a question at you guys. A, B, and C. I've got options of A, B, and C. Tell me which group is going to be the first one deprotonated from this structure, from this form of my molecule. Is it going to be group A, B, or C? This is good. This is good. Because basically, you guys have shared with me, you don't need me, and I'm fine with that. That means you are spot on. It's group C, because the important thing is we've drawn this molecule at a pH of 1. The first group to be deprotonated happens to be the C-termini. It happens to be that because that group has the lowest pKa value. Okay, so now what I'm going to do is I'm going to draw what does my molecule look like whenever I deprotonate that group. What that group is going to look like is, well, I'm going to go back to the drawing board and I'm going to go back to my backbone. N, C, C, H3 plus, H, O, and I'm going to take a pause and go back to my R group, or go down to my R group, complete that. And now I'm going to finish my C-termini. Now I'm going to label it as OC, my overall charge. Tell me what is the charge, the overall charge of this molecule, of this form of my molecule? 0. The positive and negative ends effectively cancel one another out. Now, go back to green. A, B, and C. The C termini of my molecule has been deprotonated. I can't deprotonate it anymore. So that, I'm going to erase C. My next question is, well, now which of the remaining groups is going to be deprotonated? Is it A or is it B? B. Perfect. This is wonderful. H3N plus okay. Now let's get our overall charge of this molecule. The N termini has a +1, the C termini -1, and then the R group also has -1. So what's my overall charge for this form of my molecule? -1. Okay. Are there any more groups that I can deprotonate? Add a number if the answer is yes, and a letter if the answer is no. Absolutely. I still can deprotonate the N termini of my molecule. And now I'm going to get my arrow, go back to red. I'm going to say NH2 CH O minus CH2 CO minus. Now, last few questions about this last form. What is the overall charge, or the OC, of this form of my molecule? -2. Can this molecule be deprotonated anymore? Are there any other ionizable groups where I could remove a proton? Nope, there are not. Okay, so now my question is to go back to that question that we had a little while ago. How many different forms of this amino acid, aspartic acid, exist across the range of pHs, across a pH gradient? How many forms are there? 4. Now, what I always like to do is I like to show my arrows, my kind of equilibrium arrows between different forms of my molecules, and I like to fill that in by adding my pKa values. 2.10, 3.86, 9.82. I'm going to label my different forms, and I hope that you see the similarities between what we talked about yesterday and this. C and D. A question that I'd like you guys to respond to is, let's say that my pH is or my solution pH is 3.86. I've made a, or I've adjusted, let's say I started with a pH of 1 and then I added more base, and I've adjusted my pH to 3.86 exactly. My question for you guys is, of these four different forms, A, B, C, and D, which ones are the most abundant when my pH is 3.86? B and C. Effectively, A and D, they're not in there for all intents and purposes. There might be 1 in a trillion, but there's a negligible amount of A and D in that solution. Now let me change this question. I'm going to adjust my pH to 3.87, and I'm going to change my question. Which is the most abundant form of this molecule? C. Okay, great. If my pH is 3.87, it's pretty reasonable to say, okay, well, there's about 51% C and 49% B. If I adjust my pH to, and that's not a hard and fast number, but I've shifted it. I've shifted the equilibrium to favor C. If I instead drop my pH to 3 point, I'm going to say 3.7, what do I have in that solution? There, I'm taking a general step. If I adjust my pH to 3.7, what forms of my molecule are in there and are most abundant? B and C again. Which one, or is there one that's more commonly found? B, absolutely. Now, if you understand that, that's going to put you in a very good place. One of the things that I've noticed over the years that people have a tendency to get tripped up on is they fall into this habit of looking at and saying, oh, well, the C termini gets deprotonated first, and then the N termini gets deprotonated last. Let me just caution you, that is not always the case. Do we care about if it's the N termini or C termini? We don't. What we care about is, what is the pKa? Is the pKa, or sorry, which is the lowest pKa? We want to arrange our pKa's in a sequence so that they get deprotonated in that specific sequence. Now, with that in mind, I told you a little while ago that glutamic acid and aspartic acid were our polar negative amino acids. Well, tell me this. Which form of my molecule is most common at a pH of 7? C. What is the charge of the R group on this molecule in molecule C? -1. So whenever you see that and you say, oh, that's the polar negative residue, well, that's because this definition is what's used. At a pH of 7, well, this molecule has an R group that's negatively charged. Okay, now this is the exact same thing for basically every amino acid. You go through the exact same sequence. Now, personally, whenever I draw amino acids, I like to draw them in the way that I've shown, where I display all of my atoms. I don't particularly like to do skeletal structures, but I know that some folks are more comfortable with skeletal structures. Now, to accommodate that, I'm going to share with you a tool that I think is very helpful. But before I do, I want you to know that the pKa values that I give you here are the pKa values that I will give you on your quizzes and tests anytime that it's relevant. Now, I say that because if you go out and do a Google search for amino acid pKa values, those numbers might be slightly different from what I'm showing you here. pKa values are empirically determined or experimentally determined, and different resources or different sources are going to have slightly different numbers. That's one of the reasons I never want anyone to feel compelled to memorize their pKa values or the pKa values for amino acids. Now, what I think is a really good mechanism to practice amino acids and visualizing amino acids at different pKa values is this right here, pepdraw.com. I've added the link to the chat. Right now, all that we've talked about are 5 amino acids, our polar negative and polar positive amino acids. Our polar positive amino acids are arginine, lysine, and histidine. Our polar negative amino acids are aspartic acid and glutamic acid. Arginine has the single letter code of R, lysine has the single letter code of K, and histidine has the single letter code of H. This tool right here allows you to get or visualize the structure of a single amino acid at a preferred pH. So I'm going to draw histidine, or actually I'll go with arginine, R, at the pH of 7. Draw peptide. That's what arginine looks like at a pH of 7 using the skeletal structure. Now, what can be kind of tricky about this is translating, and this is where my mind kind of struggles, translating from the atomic structure that I prefer to the skeletal structure. Positioning your, like mentally finding, okay, this is the N termini, this is the C termini. This is my R group there. Now, what you can also do with this tool is you can adjust the pH. Let's look at a pH of 3.144. Yeah, that number. pH unit is invalid. Okay. 0 to 13.99. So I think that gives me 3.99. Let's check that out. Peptide. Okay. It looks the exact same at a pH of 3.99 as it does at 4.50. When you go all the way to pH of 1, the molecule changes because it gets protonated. Okay. We are going to ultimately use this tool, or it's going to be beneficial to you to use this tool whenever we start drawing peptides. Peptides are the polymers of amino acids. And there's a slight definition difference between a polymer and a polypeptide and a protein, but we'll get more into that next week. What I'd like you to do, and what I think is a really good idea, is to go through looking at these different ionizations. So we did aspartic acid, glutamic acid. A little bit of a spoiler for you, it's going to look almost the exact same. Aspartic acid and glutamic acid are both triprotic acids. They are both polar negative amino acids. They are both going to have a -1 charge at a pH of 7. They are both going to have the extreme of, well, they can be +1 or, to the other extreme, -2. They are never going to have a charge of +2. They're never going to have a charge of -3. Now, what I want you to do is let's look at lysine. Lysine, I'm sharing the right thing, right, Joel? I knew it. Good. I knew it. Didn't make a mistake. Lysine, we're going to work through this because lysine is a polar positive amino acid. If this is polar positive, what is the overall charge of this form of the molecule? Add that to the chat. Yep, +2. Follow-up question. How many different forms of lysine are possible? We've got 3 pKa's. 4. Okay. Now, our pKa values. The C termini for lysine, okay, well, no, that's histidine. Lysine, K is the single letter code for it. The N termini of lysine is 8.95. The C termini is 2.18. The R group is 10.53. And if you're looking at that and you're thinking, how did I come up with those? How did I apply those? Well, in this chart, the N termini, I've listed that as pKa of NH3. The C termini is pKa COOH. And then last but not least is pKa of R group. That's how this chart is established. Now, if this is what the molecule looks like at a pH of 1, then what's it going to look like at a slightly more basic pH? Well, NCC. N termini is protonated. Alpha carbon. Then my R group, watch this. We've got 4 CH2s and then an NH3. I'm going to simplify that. CH2 and then NH3 positive. I'm going to put the CH2 in parentheses. I'm going to give a subscript of 4. Then what I'm going to do is I'm going to draw where I've deprotonated my C termini. I'm going to write my pKa, 2.18. If I've adjusted my pH to exactly 2.18, I've got 50% of the molecule looking like it does with the blue background, and then 50% of it looking like the other form, where the C termini has been deprotonated. I'm going to put a check mark by my C terminal pKa. Now I'll take a pause just so everyone can, I can get a response. If you're keeping pace with this, add a number to the chat. If you're not keeping pace with this, put a letter. Okay, great. Awesome, guys. You guys are doing great. The next thing that I'm going to do is draw my arrow to my next form of my molecule. The next pKa that I've got, my next lowest pKa. Oh, it's 8.95. Okay, cool. Do I care where that comes from? Not really. It's a number. I'm picking the next lowest number. 8.95 happens to be it. Oh, but now I want to look at and say, where is that coming from? I deprotonated my C termini. Now I'm deprotonating, lo and behold, my N termini. That's different from the other amino acid. But do I really care? Am I trying to figure out what's the trend? No, I know what the trend is. The trend is to deprotonate those groups with the lowest pKa's first. So now I'm going to draw my backbone. This is where I run into, or could run into, a problem. My backbone is NCC. I'm going to draw in my C termini, deprotonated. Now I'm going to draw my N termini, deprotonated. The N-termini deprotonated is just NH2. Dropped a proton and moving forward with my life. Then I'm going to draw my R group. My R group remains protonated, CH2, and then a 4, and then NH3, and a positive charge. I'm going to put a check mark by the 8.95. Then I'm going to draw my arrow, and I'm going to grab my last pKa, my lowest remaining pKa, which happens to be my only remaining pKa, 10.53. And I'm going to write this out, NCC. My C termini, my alpha carbon has a hydrogen, my N termini is NH2, no positive charge. Now my R group, CH2, 4, and then NH2. And if you're really attentive to details, you might say, oh, well, I've got to have lone pairs of electrons there. You do. But omitting those isn't really losing out on the forest for the trees. Because you know those lone pairs of electrons aren't a full-on negative charge, they're a partial charge. So we're not going to lose any sleep over that. Now, let's go back through and chronicle everything that we've done. We've drawn our 4 different forms of our molecule. We have listed out all of our different pKa's. The next thing that we want to do is calculate our overall charges for each molecule. The very first one, we gave it an overall charge of +2 because our N termini and our R group both had positive charges whenever the molecule was drawn at a pH of 1. My next form of my molecule. The next form of my molecule, well, I'm going to switch colors so that I don't mix anything up. My C termini has been deprotonated, accounted for. My N termini is protonated, and the R group is protonated. So +1, -1, +1. My overall charge for this molecule is +1. My next group that I'm deprotonating, whenever I go to that pH of 8.95 and then I go above that, my next form of my molecule. Well, in this form, my C termini still deprotonated, my N termini deprotonated, my R group deprotonated. This is going to have an overall charge of, well, this is NH2 is neutral, so no charge. C termini is -1. My R group is +1. So -1 and +1 cancel one another out. We're looking at an overall charge of 0 on that. Then last but not least, our N termini, our C termini, and our R group are all deprotonated. The N termini and C termini have no charge, but our C termini has the overall charge of -1, or sorry, has a charge of -1, and that kind of steers the ship. That means our overall molecule has a charge of -1. I'd like to get a response of letters for, hey, I'm still mixed up, or a number for, hey, I followed all of that. Okay. So we have countered the polar positive and polar negative amino acids from one another. We played both of those off one another. The process of drawing them in these different environments is the exact same. That's one of the reasons that I like to start with my molecule fully protonated, because then I go in one direction. And I do that because I love the pop group One Direction. As long as I can bring up One Direction and Zayn and Harry Styles, I'm in good shape. I actually don't. Those are the 2 people that I know of in that group. And I don't know if I said it might not be Zayn. It might be Zai. I don't know. I know who Harry Styles is, though. At any rate, I like to do this where I'm going in a single direction. There's no ambiguity in this way. To me, it reduces the ambiguity and reduces the confusion that I would otherwise have and that I had when I was drawing these structures. Now, This gives me the entire lay of the land where I can say, oh, okay. If it's in a pH of 13, which form do I have? Well, I've got the form with an overall charge of -1. Well, what about a neutral pH? Do you mean like 7? Yes. Okay, well, the most common form is going to be a charge of +1. Are there other forms of that molecule present? Yes. If the pH is 7, well, it's going to be like 99% has a charge of +1. And something like point or something like 1% has a charge of 0, or 0.5% is 0 and 0.5% is +2. But this is helpful for me so that I can say, okay, well, I know what I'm looking for. At a designated pH, that's going to be the most common. And then I can say things like, well, I know that lysine will never have a charge of +3. Similarly, I know that lysine will never have a charge of -2 because I've drawn the entire spectrum of forms of this molecule or forms that this molecule can take on. And by looking at the polar positive and polar negative residues, I'm able to avoid things like, oh, what's my trend? I go deprotonate C termini, then R group, then N termini. No, do not fall for that trap. That's the thing that people do whenever they learn their non-polar residues first, because, well, they deprotonate the C termini, then they go to the N termini. And that will make a little bit more sense tomorrow. But we don't care about N termini versus C termini. We care about which group has the lowest pKa value. That's the important part. Okay. I'm going to go ahead and stop there. It's a little bit earlier than yesterday, but this was what I wanted to get through. I would recommend that you kind of play around with this yourself. Play around with PepDraw and, try to visual like that can be a little quizzing mechanism where you say, okay, I'm going to draw it at a pH of 7. PepDraw, what do you got? Oh, okay, cool. That matches up with mine. But other than that, thank you guys for coming to class. Thank you. I hope that the number versus letter system's working well for you. I'm happy with the responses because then I'm getting some responses. Um, and I know it's very tempting for me to ask like, well, tell me about blah 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 blah, and that's just like, do you really want me to type a response? I could email it to you. I think as a student that might be like what are you really wanting that? Um, or you, the professor. But at any rate, thank you guys so much for coming to class. If anything comes up, shoot me an email. And yeah, if you've got questions, I'm gonna stop the recording. And if anyone has questions, you're welcome to hang around and I'll go through them. But if not, I'll see you tomorrow.